Think about it. Match each integral with the solid whose volume it represents, and give the dimensions of each solid. So we'll only do the first part, the matching part. Um, we have a right circular cylinder, we have an ellipsoid, we have a sphere, a right circular cone, and a torus. And then we have these five expressions there that we need to um, match one by one. I think when I see an exercise like that it's easier to go from the expression here to there, because I know a little bit how to work with that. First of all, when I look at these and they all have the same kind of aspect, it's always pi times something squared. And we've talked a lot about the fact that we write pi of f of x squared dx, which corresponds to the integral of pi r squared dx. So I recognize this as the area of a circle, and so I'm going to be able to find what the radius is. The radius is given by f of x. So what it means is that I can look at what's inside the parenthesis, ignoring the square, and see that this is f of x. When I see f of x, I'm going to then be able to kind of draw what the volume of revolution is, and I'll be able to link it to A, B, C, or D, or E. Let's try with the first one. So I got pi times f of x squared. So f of x is this thing. What does it look like? It's nothing but a linear function. R and h are constants. So this is, for example, it's maybe f of x equals 2x, f of x equals 3x, f of x equals 1/2 x. So it's a line that goes through 0. Therefore, when you rotate this line about the x-axis, what do you get? A cone. So 1 is the right circular cone. I'll cross it to know that we're done. What about 2 here? This time it's pi times f of x squared. F of x here is just r, so it's just a constant. The graph looks like this. What's going to happen when I rotate this around the x-axis? I'm going to get a cylinder. So the answer to 2 is right circular cylinder, A. Number 3, pi times f of x squared. F of x here, we've seen quite a few of those in this year, so it kind of becomes natural to recognize that as a semicircle. What happens to a semicircle when you rotate it? Of course, you get a sphere, so C. Now we have 2 that are rather difficult, this one and this one. Luckily, we only have the ellipsoid left and the torus, so let's hope it's not impossible to vaguely sketch what's happening in these 2 cases. This looks, if you have some memories of pre-calc, you may actually recognize this as half an ellipse, but anyway, it does look slightly like a circle. The only difference is we multiply or divide by some factors, a and b, which are going to squeeze or stretch the circle, and that means it's a semi-ellipse. When you rotate that, you get the ellipsoid given in B. Or if this one stumped you, maybe you can think about number 5. Of course, now we know that number 5 yields a torus because that's the only answer that's left, but we can look at that. It seems like it's a washer. We have this thing and then we subtract that one. It's actually pi f of x squared minus, again, the integral of pi g of x squared. Let's look at this. What does it look like? It looks like a circle to which, or a semicircle, to which I have added a certain value r. This graph here is a semicircle that has been moved up by capital R units. So if I rotate this thing about the x-axis, I get a big shape like that. It's flat on both sides and has circular ends. But to that thing, I'm subtracting this. What is this, g of x? It's the same semicircle, but this time with a minus sign. It's also been shifted up by r units, so I'm actually subtracting this semicircle. So now what happens when I think about this circle rotated in 3 dimensions around the x-axis? I get this kind of torus. I'm not sure I'm going to be able to draw it properly, but it's this kind of bracelet. So that answers E, and if we could find that, then we could solve the enigma of question 4, which was the ellipsoid. So hopefully one of 4 or 5 was understandable. (72b) is a question with cross sections. Find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4, and with cross sections taken perpendicular to the x-axis. Cross sections in question B are equilateral triangles. So here's the image of the volume. Note that the x and y axis are positioned a little bit strangely. We'll change that when we make our sketch. Okay, so here's the circle x squared plus y squared, and we have cross sections perpendicular to the x-axis, and all of these are equilateral triangles. So, what's the base of my equilateral triangle? This is y, and I have another y below. So when I want to find the area, I have 2y, 2y, 2y. I need to find the height of the equilateral triangle. Let's call it h. This is y. 2y is the entire base. So h equals the square root of 2y squared minus y squared. That's 4y squared minus y squared equals 3y squared equals root 3 times y. So what's the area of the equilateral triangle? It's base times height over 2. That is root 3y squared. So in every case, when we are looking for a volume, we can take the integral of the area. Actually, this time the area is in terms of y here, but I'm going to need to change that very quickly. So it's the integral of root 3y squared dx. I'm going to need to fix that, and then I'm going to need to decide what my bounds are. So what is y squared? I need it in terms of x because it's a dx. So actually it happens that it's easy to find. Y squared is 4 minus x squared. I don't even need to go to y and then square it again. It's already y squared here. So I'm integrating root 3 of 4 minus x squared times dx. So what are my boundaries? I'm starting all the way here, and I'm going all the way there. So I'm going from negative 2 to 2, from x equals negative 2 to x equals positive 2. So let's just solve that. I can put the root 3 in front. Why not? 4 minus x squared dx equals root 3 4x minus 1/3 x cubed, evaluated between negative 2 and 2. So I can plug these numbers in. If I plug 2, I get 8 minus 8 over 3 minus negative 8 minus 1/3 of negative 8. So it's actually plus 8 over 3. So here I have 8 minus 8 over 3, and this is also 8 minus 8 over 3. So it's 2 times 8 minus 8 over 3. Let me just calculate 8 minus 8 over 3, 24 over 3, 16 over 3. So this is also 16 over 3, so together 32 over 3. Root 3 times 32 over 3. That's my answer. 32 root 3 over 3 is the volume I was looking for.